Okay, hi everyone, welcome back. So lately we've been doing lessons on rules for differentiating different kinds of functions, and this is going to be a lesson on derivatives of trig functions, because we haven't really learned like what's the derivative of sine x, what's the derivative of cosine x, things like that. And then of course, what we're going to do is establish rules for these, and once we establish them, we could also combine them with the other things we know, like the product rule and the quotient rule and all of that. Okay, so let's go ahead and get started. All right, derivatives of trig functions. So let me start by saying, so far, we have derivative rules for lots of different kinds of functions. First of all, we learned how to do derivatives of polynomials. We learned how to do derivatives of root functions. That would include things like the square root of x, but also you could do the cube root of x, right? Just think of the cube root of x would be x to the 1/3. You'd use the usual rule for x to a power. And recently we've learned how to do derivatives of products and quotients. I would say that we haven't really learned all products and all quotients. Like what if there was some, what if part of the function was something we haven't looked at yet? But we've learned how to do a lot of products and a lot of quotients. And then we also learned how to do the derivative of y equals e to the x. That was a good one. So our goal is to have derivative rules for as many functions as possible. And of course, next is trig functions. You know from previous classes like pre-calculus or trigonometry, you know that trig has a lot of uses. So it would be useful for us to be able to differentiate and find the rate of change of trig functions. I want to start by saying, note, in calculus, we always work in radians unless specified otherwise. So I'm not going to go into a big discussion about what the difference is between degrees and radians, because you should know that from prerequisite classes. I am telling you that we need to work in radians, that's kind of the more natural measurement. And the only time that we might see degrees would maybe be in a word problem if a problem specified degrees. But otherwise, we need to think about radians. Now, when we derived a lot of our derivative rules, like the product rule and the quotient rule and the rule for e to the x, for a lot of them, we turned back to the original definition of the derivative and we used it as a starting point. For the trig functions, we're not going to do that. We're going to use more of kind of a visual argument, and I'm going to use the graphs of sine and cosine to kind of try to convince you of what the derivative function is. So this might seem a little bit less rigorous, maybe, but I think that it's a good way to kind of get an intuitive understanding of why these derivatives are what they are. So if f of x equals sine x, what is f prime? That's what we're going to start with. And I'm saying we're not going to set up the limit as h goes to 0 and do all that. We're going to look at the graph instead. So I'm going to draw a picture of the graph of sine x, and I'm only going to draw probably one period. You remember the graph of sine x, go up to 1, -1. Let's say this is pi, and that would mean over here is negative pi. Passes through the origin, right? Now that I think about it, I didn't really set this picture up exactly to scale. I think we'll probably just say it's close enough. I was thinking, pi is a little bit bigger than 3. I was probably going to set it up to be kind of the same scale vertically and horizontally. I don't think I exactly did that, but we'll say it's close enough. We'll just imagine it. Here's pi over 2. Here's negative pi over 2. All right, so you know that from pre-calculus. This is just the graph of f of x, right? The graph of sine x. And I'm saying that we could figure out some things about f prime by looking at the graph of f. For example, if I were to ask, based on this graph, we see, can we figure out f prime at some specific values? I'm going to set up 5 values for us to think about. And I'm not asking for f values. That would be easy. I'm asking for f prime values. Based on the graph of f. Here's what I'll do. I'll get another pen. I'll get my blue pen out. We'll think about the slope of the tangent line. All right, how about f prime of negative pi? So we're looking at, here's negative pi, and we're asking what's f prime? Well, f prime would be the slope of the tangent line. So the tangent line here looks something like this, right? This blue line. And what do you think the slope of that is? So it's definitely negative. As you go from left to right, it's going downwards. So it's definitely a negative. I'll put a minus sign here. It's definitely minus something. For every 1 unit I go over, how many units do I go down? I think that the slope of this blue line looks like -1. I think it looks like it's making a 45-degree angle with the x-axis. I think for every 1 unit I go over, I would go 1 unit down. I think -1. For f prime of negative pi over 2, we're looking at this part of the graph, and we're asking what's the slope of the tangent line at this place. And I think that here the tangent line looks like it would be flat. We're at the bottom of that valley, and this just looks horizontal. And what's the slope of a horizontal line? 0. Let's look at the next one, f prime of 0. F prime of 0. So we're looking at this part of the graph, and we're asking what is the slope of the tangent line? Here's the tangent line. What's the slope of that? It's positive. As I go from left to right, the function, the tangent line is going upward. I'm going to say that's +1. If I drew this exactly to scale, perfectly to scale on the x and y axis, then yeah, it would look exactly like 1, but I think this looks pretty close to 1. Next, we look at f prime of pi over 2. So we are looking at this part of the graph and trying to figure out what's the tangent line even look like here. Remember, the tangent line needs to just kind of graze the curve at that point and pass through the point with the same steepness as the curve. Well, we're at the top of this hill, right? So we're flat again. It's just for that moment, for that brief moment, it goes flat. And that means it's horizontal, which means 0 slope. And finally, last one of these 5 is over here at pi. What's happening at pi? This is what the tangent line looks like. This tangent line looks like the first tangent line we looked at, which makes sense because you know that sine of x is a periodic function, and we've gone 1 complete period, and now it's going to kind of start repeating itself. So if we said -1 earlier, this has to be -1 also. Idea. Let's plot these 5 points for the graph of f prime of x and try to see what familiar function it is. What I mean by this is telling me that f prime, the graph of f prime, would have the point negative pi comma 1, the point negative pi over 2 comma 0, the point 0. These are all for the graph of f prime. And maybe based on knowing some points, we can get a rough idea of the shape, and then we could figure out what function it is. So I'm going to draw another picture down here. We'll try to do roughly the same scale as the other one. Why not? All right, up above I said graph of f of x. This one I'm going to label graph of f prime of x. Okay, I'll still mark pi over here, 1, -1, negative pi. So let's do mark negative pi over 2 and pi over 2. So we have 5 points from our little kind of table above, and we'll try to indicate them on here. So I think negative pi comma 1 would mean that there's a point here. We'll have to decide if 5 points is enough for us to figure out what function this is. But we get that point. Negative pi over 2 comma 0 is here. 0 comma 1 is here. Pi over 2 comma 0 is here. And pi comma -1 is here. Do we know a familiar function that passes through those 5 points? You might be able to say that there are a bunch of different functions that pass through those 5 points. Maybe 5 is not enough. If you wanted, you could find some points at pi over 4, other familiar numbers that show up in trig. Pi over 4, pi over 3, pi over 6, right? You could find sine of those, and you could find, or you could estimate the slope of the tangent line and then figure out where they would go here. But I hope if it's all right with everyone, I'm going to connect these 5 dots with a nice smooth curve. And I think we'll be able to figure out what function this is. These actually connect like this if you were to find all the in-between points. So do you know what familiar function is f prime of x? It's another trig function, right? The derivative of sine x is, here was the graph of sine, here's the graph of the derivative. It's actually cosine x. It is exactly cosine. And that would be very difficult to try to get to using the definition of the derivative. I'll tell you that, like limit h goes to 0 of the difference quotient. I don't know if we'd be able to find it that way. So based on a graph and based on an argument of what function this looks like, maybe I kind of connected the dots in the correct way because I knew this would be a smooth curve. Yeah, derivative of sine is cosine. So that is a rule that we can just use from now on. Of course, there are other trig functions for us to talk about besides just sine. So we'll move this page in just a moment. Okay, so let's move this page up and let's work a little bit on the next trig function. So we've established a rule for the derivative of sine. And now the question is, what about the derivative of cosine? Seems like a natural question to ask next. So the fact that the derivative of sine was cosine, that might make you think maybe the derivative of cosine is going to be sine. It would be really convenient if it works out that way. I'm going to tell you that it almost works out that way, but not exactly. So here's what we'll do. We're going to say g of x equals cosine x. All right, and then we want g prime of x. And we could do the same kind of strategy as what we did above. In fact, we already have a graph of cosine up here. Should we even draw another one? I guess we'll draw another one because I want to draw tangent lines and all of that. So let's do a quick graph of cosine. Graph of g of x, not g prime. And we'll say here's 1, -1. And that would mean maybe about here we'll say is pi over 2, -pi over 2, -pi, it's y, there's x. So the graph of cosine we actually just had on the screen because it was the derivative of the previous thing. So, you know, it passes through these points. Don't get the graphs of cosine and sine mixed up. Remember that sine passes through the origin, cosine passes through a y-intercept of 1. All right, we can work with this. So let's do the same kind of thing. Let's try to figure out what is g prime of some of these points. And if we find it for about 5 points, I think that's going to be enough for us to fill in the rest. We're just trying to convince ourselves of what familiar function this is going to be. So let's think about tangent lines again. I set up the same 5 values just because those are the ones that I marked on my x-axis. We could check in between stuff if we want, pi over 4, whatever. But let's just do these. So -pi, we're over here on the graph. And what does the tangent line look like here? I'm going to say the tangent line looks horizontal. Here, you know what? Let's just draw all 5 tangent lines first. Let's just do the drawings. At -pi over 2, we're here. Tangent line looks like this. At 0, we're here. Tangent line looks like this. Pi over 2, that's definitely going to be a negative slope. And over here, tangent line looks horizontal again. So what do these 5 slopes look like? This one, this one, this one, this one, this one. I'm going to say it looks like 0, 1, 0, -1, 0. All right, we'll plot these 5 points. These 5 points for a graph of g prime. And then we're going to see, does this equal like a familiar function? Does it equal sine x? Does it equal cosine x? Does it equal tangent? You know, what is it? And this is basically saying that there's the point -pi, 0, -pi over 2, 1, 0, 0, pi over 2, -1, and pi, 0. So let's draw a picture. Okay, just plotting these 5 points. So -pi, 0 is here. -pi over 2, 1, 0, 0, pi over 2, -1, and pi, 0. You see those 5 points? Goes up, down, up. It seems believable that maybe these are connected with a nice smooth continuous curve. Like this. And it keeps going, of course. We're only drawing part of the picture, but all of these pictures we've drawn today keep going to the left and to the right. And I'll say this is a graph of G prime. So can we tell from the picture, what have we found? The rule for the derivative of cosine x. It's whatever this function is that I've drawn here. Is it a function that we know? Is it a trig function that we know? Well, earlier I said the derivative of sine was cosine, and I said it would be really nice if the derivative of cosine turned out to be sine. But look at the graph of sine. This was the graph of sine. That's not exactly what we got here. They're different, right? Wait, can we see them side by side? Let's see if I can get them side by side. Look at that. So on the right is a graph of sine x. What we're looking at, this looks like a flipped upside down version. It's a flipped upside down version of sine. Do you see that? They both pass through the origin, but other than that, take this picture, flip it upside down, you get this picture. So flipping upside down means this is negative sine x. And that is going to be our rule for the derivative of cosine. So now we have a rule for the derivative of sine, derivative of cosine. We can add these two rules to our toolbox of derivative rules, and we can use them in combination with other rules as well. Let's do a problem. I'll do this one for us. I'll have something else for you later. So let's find the derivative of y equals x squared sine x. So you see what I mean when I said that we could combine this with other rules that we know. The derivative rule for sine x we talked about today, but this is a product. This looks like we need the product rule, which we talked about in a previous lesson. So this is, this needs product rule and our new rule for the derivative of sine. That's what I mean about combining new rules with old rules. So first of all, let's get started with the product rule. So we're trying to find the derivative, so we'll call it y prime. The product rule says you take the first function times derivative of the second plus the second function times derivative of the first. Next, we need to evaluate these little derivatives, d dx of this, d dx of that. So this is going to be x squared cosine x. From what we said today, derivative of sine is cosine. This stuff over here is, well, this is going to be 2x, right? Sine x times 2x, and it's going to look neater if we put the 2x out front. Do you see why I put the 2x where I put it? Imagine if we didn't. Imagine if we left the 2x to the right, then it would say sine x 2x, and it would be a little bit unclear Are we just taking sine of x, or are we taking sine of x times 2, or are we doing sine of x times 2 times x? It would be a little unclear. So if you move the 2x to the left, then there's no confusion. And we could leave the answer like this, or another way that you could write this is you could say, well, both terms involve x, so maybe you want to factor out x. That's up to you. And write the answer like this. Either answer is okay. I'll show you another one. Let's differentiate All right, I'm going to do this one for us also. This is a little bit different from some other problems we've seen. Okay. I don't know if we've seen one like this before. Well, you know, what makes this one different? What makes this different? I feel like it's different because it's a product of three things. There's x times e to the x times sine x. Usually with the product rule, we just have two things, but this has three pieces. And they're all being multiplied times each other. And all three of them are different types of functions. You know, there's x, which could be considered a polynomial. Like x is sort of a simple polynomial by itself. E to the x is exponential. Sine x is trigonometric. So we have three different types of pieces. Here's what I'm going to do. It's a product. I'm going to say product rule, where I'm going to think of this as my two pieces. Now, that's not the only way to split it up. If you prefer, you could just underline the x as your first piece and have the rest of it be your second piece. That's also okay, but the important thing is the product rule says there should be a first piece and a second piece. So set it up either way. I'm going to say first piece times derivative of the second plus the second function times derivative of the first function. And let's keep going. So x e to the x cosine x is that part. Oh, look at this. We have to use the product rule again. It's okay, we can do that. So sine x times, what's the product rule on this? Here, I'll underline the two pieces. There's the x and the e to the x as my first function and second function. So first function times derivative of the second plus the second function times derivative of the first, like that. And I tried to make it clear that we're not doing sine of this stuff. We're doing sine x times this stuff. First piece here is just going to stay the same, x e to the x cosine x, plus, we'll just leave the sine x alone for now. Let's work on this part that's in parentheses. So this is going to be x e to the x plus e to the x. At this point, maybe I would distribute, see if there's anything that's going to combine, see if there's going to be any nicer way to write this. So I decided to distribute across the parentheses here. So I wrote this as x e to the x sine x plus e to the x sine x. And then I look at all three pieces and I say, well, this one has cosine, this one has sine, so like they don't really combine, but we could factor something out. Maybe make it a little nicer because all three terms have one thing in common, and that is e to the x. So let's pull that out. E to the x pulled out of each piece leaves us with x cosine x plus x sine x plus sine x. And that's a good answer. So that's a big answer, right? But this problem was more complicated than most of the ones that we've seen because it had 3 functions instead of 2. So we had to use the product rule twice. So I'm going to give you one that I'd like you to try, but I think that I am going to get it started. So let me write the problem and then do like maybe the first step. So far, we've established derivative rules for sine x and cosine x. You might say, well, what about the other trig functions? Well, we're going to find one of them as an exercise. We are going to find the derivative of tangent x. And I don't want us to do this. I don't want to do this based on drawing. I don't want to draw the graph. I remember the graph of tan x, and we could try to work with it, but the graph of tan x is a little bit harder to work with. So it turns out that we don't need to resort to that. So here's what we're going to do. Let me get this started. I'm not going to do much of it for us. I'm just going to get started. What I'd like you to think of is, remember, there's a fundamental trig identity that says tan x can be thought of as sine x over cosine x. Now, think about the rules that we know for derivatives. And I'd like you to see if you can finish it from here and simplify your answer. And then you could pause the video and try this. Okay, so hopefully what I was hoping you would think of is the quotient rule. This is definitely a quotient. Use quotient rule, right? So we have a function on top, a function on the bottom. So let's go. Bottom function times derivative of the top function minus sine top function times derivative of the bottom. All of that is over the bottom function squared. We'll continue with this and we'll see if we can finish differentiating and simplify. So cosine x times, all right, let's do that derivative there. Cosine x times the ddx of sine x is cosine x minus sine x times ddx of cosine x. We just said that this is supposed to be negative sine x. All of that is over. You know, when we have cosine x squared, don't we usually write it like this? Cosine squared x. So let's just write it that way. Technically, we differentiated. Do we want to say that this is now the derivative rule for tangent x? Anytime we have the derivative of tangent, we write this whole thing? No, we could simplify it. We could simplify it quite a lot. So here's what I want you to see. Cosine x times cosine x is cosine squared x. That also happens to be the denominator. What about this other stuff? Minus sine x times minus sine x. Well, it's a minus, it's a negative and a negative, so that becomes a plus. Sine x times sine x is sine squared x. That looks a little bit nicer. We could simplify this a lot, right? If we were in person in class, I would be asking for students to help out with this, but what about this? How do we simplify this? This should be everybody's favorite trig identity. this whole thing equals 1. That's my favorite trig identity. I don't know about you. But sine squared plus cosine squared equals 1. So this whole thing simplifies to 1 over cosine squared x. Now we're getting somewhere. Now we're kind of simplifying. I think we could still write this in another way. This is pretty good. This is pretty good, to be honest. If you got that far, that's pretty good. But there is another way that we prefer to write the answer for this problem. This is 1 over cosine x squared, and another name for cosine, another name for 1 over cosine is secant. So the way that we prefer to write this answer is secant squared x. Now, what we just did, used the quotient rule and a couple of simple trig identities, but the main thing is we just derived a rule for the derivative of tangent. So earlier we derived a rule for the derivative of sine and cosine, and now we have one for tangent. Derivative of tangent is always secant squared x. So if you ever have a problem that asks you for the derivative of tangent, maybe as part of a product rule problem, part of a quotient rule problem, part of something else, you can go straight. It's okay to go straight to this answer. This is like a formula for us now. Derivative of tangent, secant squared. Now, there are other trig functions, right? There's 6 of them. And here's what I'm going to say. We're going to do a rules summary where I'm going to include the 3 rules that we've established, and I'm also going to tell you the other 3. So, derivative of sine x, we said that that was cosine x. Derivative of cosine x, we said that that was negative sine x. You have to remember the negative goes there. You have to remember which one gets the negative, because it looks like sine and cosine are derivatives of each other, but you have to remember the negative. And we just established this rule through that problem, that the derivative of tangent is secant squared x. Now, there are 3 more. Cosecant x, secant x. I don't want to spend as much time on these 3, but we should be comfortable with them also. Cotangent x. So, without solving these by hand right now, let's just look at these 3 and think to yourself. You don't have to do all the work, but think to yourself, how do you think you would find these? Like, how would you get started to try to find these? Well, what I would suggest is that these 3 could be found in a similar way to what we just did here for tangent. We wrote tangent as sine over cosine, and then we used the quotient rule. If you wanted to find the derivative of cosecant, you could say, hey, cosecant is 1 over sine. Remember that? Cosecant x is 1 over sine x. And then use the quotient rule on 1 over sine. And you would quotient rule get to an answer. Sine x, same thing, except it's the reciprocal of cosine. Cotangent, there are 2 ways to do cotangent. First of all, cotangent is the reciprocal of tangent. So you could do it as 1 over tangent and then quotient rule. Or you could say cotangent is actually the flipped version of this. So instead of sine over cosine, it's cosine over sine. And again, you would use the quotient rule. So I'm going to tell you these 3 results. This one is negative cosecant x, cotangent x. This one is secant x, tangent x. And this one is negative cosecant squared x. And I guess what I want to say about these 6 rules that we have here is, for these 3, I expect you to know these. definitely, memorize these three. Sine, cosine, tangent come up. They come up a lot. These other three, I'm going to say, I don't think that I'm going to say you have to memorize these ones. I think that if you ever needed to know, like if you were ever in the middle of a problem and you needed to know the derivative of secant x, I think you could always find it using the quotient rule. Like, how much work did this take us here? It's not that bad. So you could always find these three if you needed to. So don't worry so much about memorizing these. However, I am going to say proving these three would be good practice. I think that those would actually be good practice rules for, like, good practice quotient rule problems. But there they are. There's the 6 rules for derivatives of trig functions. I do have one more problem for us before we go. So if you've gotten those rules written down, then we're ready to move this page. Look at that, we could still fit it on the screen. All right, so I have one that I'd like you to try. I'd like to say, given f of x equals tangent x over e to the x, I want you to find f prime of x. So I'd like you to pause the video and try to find this and simplify your answer. Okay, so, earlier we did, or I guess I did, a couple of problems that used a combination of the product rule and the new rules that we've said today for derivatives of trig functions. This one's going to use the quotient rule and derivative of a trig function. So let's get started. F prime of x equals, it's a quotient. We have to use the quotient rule. So bottom function times derivative of the top minus sine top function derivative of the bottom. All of that is over the bottom function squared. Don't forget that. Let's keep working with this and see where it leads us. It's not going to be that bad. We know the derivative of tangent x is secant squared x minus, what do we have for this thing here? I mean, the derivative of e to the x is just itself. Let's put that to the left of tangent. So, it was to the right, but when I took the derivative, I prefer to move it in front. Whenever there are trig functions involved, I kind of prefer to move things to the left of them so that it doesn't look like I'm doing tangent of x e to the x, right? It's clear that I'm only doing tangent of x because the e to the x is here. All right, on the bottom, we've got e to the x squared. Is there anything further that we can do to simplify? What do you think? I see something. I see something we can do to simplify. How about the fact that this piece has e to the x, this piece has e to the x, this piece has e to the x squared. So what if we cross out, e to the x, and cross out the squared? Then we get secant squared x minus tangent x over e to the x not squared. And that is a good simplified answer. So sometimes, a lot of quotient rule problems, a lot of times with the quotient rule, because the quotient rule always has the bottom part squared, a lot of times the answer will still have the bottom part squared. But if you're lucky, you find something that helps you cancel it out, and you might get something like this. It's even simpler. All right, I'll give you just another moment in case anyone is copying that down. All right, before we go, I have something important to say. I have something important to say. Uh, you've probably heard me say something like this before, but the next lesson that we have is very, very important. Okay, so make sure you don't miss the next one. It is called the chain rule. I'll tell you that in Calculus 1, the way that I think of it is that there are three big rules, and it's the product rule, the quotient rule, and the chain rule. Now, we've already done the product and quotient rule. We did those together as one section. But the chain rule is so important that it gets its own section. It gets its own lesson devoted entirely to this one rule, and we're going to use it for the rest of the semester. So make sure that you pay close attention to that next video. All right, so hopefully everybody's getting in some practice on the quotient rule and product rule, and now these trig function rules. And yeah, we'll be ready for the next video. So that's all, and everybody take care. I'll see you soon. Bye.